Continue the PCS?
No.
No? So it's
We start a new topic today.
Right.
Actually, about the BCS, I have a bit more to say, but we don't have time for this, so I'll send a message about it, but there is a summary in the lecture notes that I recommend you to read, but we basically covered the main things. Okay, so I will start.
Before we continue, please
yeah.
pull down
I have no idea how to do it. Let me see. I don't know how to work these things. Wait. I never understand the logic. Anybody?
I can just move.
Okay. I hate these things. Yeah. It's also very hot.
לא בשבילנו.
Oh, okay. Okay, there's progress. I don't know what I'm doing, but there's some random walk. I hope this is enough. Okay. You want to try? But try not to go back because you already achieved something. No. Yeah, that's a good one. Oh, great! Thank you. Thank you. Okay, so today we're going to start a new subject, which is the subject of a path integral. I'll tell you today what it is, and basically it's an alternative formulation of the quantum mechanics, which has some advantages. Both in terms of understanding and interpretation, and also in terms of a calculation tool. What we are going to do today is to start from a quantum mechanics problem of a single particle, which we already know how to deal with using operators and representing wave functions in terms of vectors and all that, and solving Schrödinger equation. But we just take a generic problem of a quantum particle and reformulate it in this path integral picture. This is developed by Feynman. Okay, and then later we'll see that we can generalize it to many body quantum problems, and it's actually going to be a very useful tool that allows us to calculate things systematically, and even go beyond, for example, the mean field approximation that we discussed in the previous lectures is an approximation that we use in many problems. Sometimes it's good approximations, sometimes not. But what if you don't know? You want to go beyond the approximation and see how important are the corrections. This is very difficult to do in the formulation that we used up till now, but in the path integral there is a suggested way of formulating it that is very useful. So I'm going to go back to single particle quantum mechanics. We have a quantum particle described by Hamiltonian that is quite generically a sum of two terms, kinetic energy and potential energy. The operator T is some function of the momentum operator, and V is some function of the coordinate, which I represent by Q. And we know that Q, P are non-commuting, right? So they obey the canonic commutations, IH bar. Okay, so this is the standard quantum mechanics, and we also assume one-dimensional problem. So we have a particle in one dimension, there's only one coordinate, Q, and a momentum conjugate to it. And this kind of problem you already saw many times. So what we're typically interested in is solving either a time-dependent or a time-independent Schrödinger equation. Okay, so basically this is the solution. What we're looking for are wave functions that are solutions of Schrödinger equation, and we learned, or you learned in previous courses, how to deal with it in various cases. Now, one of the difficulties is that when we work with operators, and especially if we are interested in time evolution, in finding the time evolution of a wave function, so problems like you prepare some state, and now you evolve it with some Hamiltonian that maybe you can even imagine switching on at some point, and you want to see how this evolves. And the solution is often complicated, and the path integral suggests a way to deal with it that somehow goes around the fact that what is the main difficulty is the fact that we have non-commuting operators, and if we imagine a problem where we have to apply an operator over and over again, we have to multiply many times operators that do not commute and keep track of their commutators, and it can become complicated, okay? So this is the problem that we're going to focus on, and I'll show you how to use the path integral, and the main idea behind it is to convert it to a problem where I can forget about operators. Of course, what does it mean to forget? There is a conservation of difficulty. So you are replacing one difficulty by another. The price we'll have to pay for that is that we'll have to solve integrals that are multidimensional. But sometimes dealing with complex integrals is, in a sense, easier, and I'll discuss particular examples. Okay, so let us imagine the following problem. I have, this is my coordinate Q, it's one dimension, and I have some position Qi on this axis, and I prepare an initial wave function that is a delta function localized at Q, okay? So I take it's basically a wave packet, I prepare it in a state that is localized on one coordinate Qi. Now, this particle, this quantum particle, experiences a Hamiltonian. It's a solution of this Schrödinger equation which contains a kinetic energy. Therefore, such a wave function is not an eigenstate of the Hamiltonian, right? Because of the kinetic energy, if I now evolve this state in time, it will acquire some time evolution which will change the structure of the wave packet, right? And typically what will happen to it is that it will expand, okay? In the extreme limit that we have just zero potential or constant potential and just kinetic energy, a free particle, we know that the eigenstates are actually extended waves, right? So it's very far from this localized wave packet. So the state will expand. More generally, if there is a potential, it will evolve to some other wave packet. So if I now add here another axis that describes the time, okay? And at each instant, this is t equal 0, okay? And let us look at some final time that I denote as capital T. And the question I would like to ask is, if I let this particle evolve in time, evolving with, under the influence of a particular age, what is the probability that I will find it after some time t in some other location, okay? Either in the same location or some other location. So that's the question that we are asking. If I look at the coordinate axis after some time, actually if I look at particular time slices, okay, let's think of it like this, then at slightly later time, the wave packet will become something like that, and later it will become something like that, and then we are interested in what happens in the final state. It will now become, okay, something, let's say, I'm being very general, and now I define now some other coordinate, QF, okay? And what I ask is, what is the amplitude of this evolved wave function, time evolved wave function? What is the amplitude for it to be at QF, okay? And we know that the absolute value square of this will give us the probability, okay? So, so this is the problem, and let's look at it like this. So I define the problem as follows. I have some initial state at time equals 0, which is the state Qi, okay? What is this state? It's a state that in real space looks like a delta function, Q minus Qi. Okay, that's the state Qi. And then the same state is evolved with time, and at time equals capital T, it is given by the solution of the time-dependent Schrödinger equation, which is e to the minus I h t times Qi. Okay? You are familiar with this, right? Okay, so this is the time-dependent wave function after time capital T. And if I want to ask the question, what is the probability for the state to be equal to QF? That's actually the question that I'm now asking. So I'm going to define something that is called a propagator. Okay. We denote it by G. It's a function of 3 variables. Okay, this is how I write it. Okay, it depends on the initial coordinate, the final coordinate, and the time between the time of the time evolution. And the definition is the inner product between psi of capital T with QF, okay? Or in other words, if I plug in this explicit time evolution, it's the matrix element of the operator e to the minus IH T between the initial and the final coordinate states. Okay? So we can think of it as a matrix element of some operator, and it's the time evolution operator. Okay. Now, again, as I said, for a general Hamiltonian, which has both kinetic and potential energy which do not commute, this is a difficult problem. Okay? But, and here's the idea that Feynman had. Let's think of it this way. Just solving this problem in general is complicated in the tools that we know from basic quantum mechanics, but we know that if the time t was very, very small, then we actually could have, to a good approximation, get the result very easily. Why is that? Because the commutators can be under control in some way. And let me mention a very important formula. This is a general mathematical formula that is called the Hausdorff-Baker formula. I'm not sure I know how to spell Hausdorff and Baker, but I'm just calling it HB formula. Okay, and it says the following. Suppose I have two operators, A and B. The exponential of A plus B is, so if A and B were just numbers, what is the exponential of A plus B? It's e to the A times e to the B, right? But because they are operators, let me put heads here to make sure that these are indeed operators. This is no longer true, right? And actually there are corrections, and the correction is that you have to subtract a commutator. Actually, here I'm assuming that the commutator of A and B is a C number, okay? Otherwise, they're actually corrections, okay? So they're also commutator of a commutator and so on. It's generally an expansion, but okay. So actually, to be more general, there are actually corrections to it. But now, so this is a formula that sometimes is useful. In the case that A and B commutator is just a C number, it's very useful. Sometimes there are many corrections and it's not a useful expansion. But notice that if there is some parameter by which A and B are small, okay? They're small, so that we can actually expand the exponent to a power series, and we know that higher powers are negligible, or can be at least subdominant. Then we notice that the commutator is already quadratic in this small parameter, and therefore we can neglect it, and all the other corrections are even higher order. Okay? So, in other words, the main difficulty with this operator is that it's an exponential of an operator, and the operator itself contains a sum of two things that are non-commutative. So, but we could have neglected this correction if the A and B were small. Now, in general, they're of course not small, but the trick that Feynman suggested is the following. Let us divide our time evolution to time slices that are very, very finely sliced. Okay, so we imagine, of course, there is a continuous time evolution, but let's divide the time to time steps, very small time steps. I define here dt to be capital T divided by n, where n is an arbitrary, very large number, and in the limit that n goes to infinity, dt will go to 0. Okay? So, what we suggest is the following. Let's write down this operator as a product of many time steps, okay? So we first evolve the state in time dt, then 2 dt, 3 dt, and so on until we get to the end. Now notice that because the only operator that appears here is h, I can write this exponent as a product of e to the minus ih dt. This is a single time step to the power n. Okay, and that's an equivalent. Okay, so we can think of the exponential of minus iht as e to the minus h dt times n, capital N. Okay. Okay, so that's what we do. Now, why does it help me? We're going to do the following trick. Let me take just one of the time steps. Okay, so I now take this operator and I write it. Okay, this is the first, and then I have a product of many replicas of the same thing. And now I have somewhere in the middle, okay, I have a product of capital N times the same things. Now here, somewhere in the middle, I want to write it as minus I t plus v dt. Okay? And again, and so each of these terms is actually an exponential of a sum of operators t plus v. Okay. Now, the next step is the following. Because dt is small, okay, and we are going to define everything in the limit that dt goes to 0, I can do an expansion in dt such that this exponent can be substituted by a product of two exponents, one with only t and one with only v. Okay, so this is what I do. Let's write it down. I'm going to use the Hausdorff-Baker formula, and I write it as e to the minus I t dt, e to the minus I v dt. And I know that there is a correction, but the correction has in the exponent something that is of order, okay, or let me not even write the I, it's something of order dt square, okay? Okay, so right, because it's going to be the commutator, at least the first term in the expansion is the commutator of t and v, but with a factor dt square, right? And therefore, in the limit t goes to 0, we're going to neglect this part and maintain only the terms that are linear in dt. Okay? Okay, so this is what we do. And again, the procedure is exact only in the limit that dt goes to 0, which means that n goes to infinity. Okay? Okay, so this is actually what we're doing, just to make it clear. We divide the time capital T to slices of size dt, and we're going to go to the limit that they become almost a continuum. Okay? All right, so, okay, so after I'm done, so, and now it's going to be an approximation. When I'm done with this stage where I neglect the commutator correction, I'm going to get a string of a product of many, many operators, e to the minus I t dt, e to the minus I v dt, and again t and again v, okay? Alternatingly, let me write it explicitly. With your permission, I erase this t. Okay, so I have e to the minus I t, e to the minus I v, and then somewhere in the middle, I again have e to the minus I t dt, e to the minus I v dt, and then again e to the minus I t dt, and so on. Okay, until I end with, in the end somewhere, I have, okay, I keep track of the order in this way, okay, just for convenience. Very good. And okay, so what did I gain by this? I have an infinite or a multiple product of operators alternatingly, and I leave it like this. It's still an operator. What do I do next? Now the idea is I want to get rid of the operators. How do I get rid of operators? I take the matrix elements in states in which they are diagonal, okay? Because I know that there are two basis states that I can choose in this problem. Either states that are states like Q that are localized in space, coordinate, or states P that are plane waves that are eigenstates of the kinetic energy. Okay, so namely, I know that I can. I have the following expression that T acting on, so T acting on P is just the classical expression for the kinetic energy with momentum P times P. Okay, so P are eigenstates of T, and Q are eigenstates of V, right? Okay? Because V is only a function of Q and T is only a function of T. Okay? Okay. So how does it help me? It helps me in the following way. I'm going now to take each pair of such operators, and let me assume that somewhere here this product is, I give it an index n, where n is between 0 and capital N. Okay, so let me define an index that measures the particular time slice somewhere in the middle of my path. So it's between n and 0. Okay. Okay. So what I'm doing now is we learned in the previous classes, and used it many times, that I can always define a resolution of identity. When I'm writing a product of two operators, I can always put one in the middle, right? This you can always do. But this one, which is just the identity operator, I can express it as a sum over all the projections to a full Hilbert space. And for any single body states, I can write a resolution of identity. Where shall I write it? Let's do it here. So for any complete set of states, the sum over all lambda of the projections is the identity. Okay? Okay, and which means that I can plug it anywhere I want and replace it by the identity. So that's what I'm doing here. What I'm doing is to take in the middle between these two operators, I plug in a resolution of identity. But what can I choose for my lambda? I have two options. either P or Q, okay? One of them is going to be the eigenstates, a basis of eigenstates of V, and one of them eigenstate of T. But I have both V and T, so what do? I can always write the resolution of identity as a product of two identities, right? So this is what I do. I'm introducing here an integral from, let's say, minus infinity to infinity, because I have infinite lines of dp, let me call it dpn, and I also integrate over all qn along the line of q of, now I'm introducing two projectors. So P and Q. Okay? Is this clear? So it's just a product of two identities, two resolutions of identities. Now, and I put here an index n to denote that I do it for in between the two operators in the nth step. But I will also have the same thing exactly. And I can also, I can also introduce, let me see. I can also introduce this resolution of identities in between the two, these two operators, okay? And I can do it repeatedly, and each time I'll have an integral over some intermediate momenta and coordinates. I'm allowing them to be anything, but I introduce these projectors, okay? So, and I do this, I sandwich between each two operators, I sandwich such a thing so that after I'm finished, I no longer have operators, I just have matrix elements of operators, and they are defined in such a way that the operators that are sandwiched between them are diagonal. Okay, so what happens? First, let's look at e to the minus it dt. When I apply it on Pn, what do I get? I just get, because it's this is an eigenstate of this operator, I just get a number, e to the minus it of Pn times dt. And similarly, here, if I now plug in, let me write it like this. I just want to check something that I do it in a convenient, so okay, so this way. So here I can now plug in an integral of qn minus 1 integral dp n minus 1, and I plug in here sorry, wait. Yeah. me actually, okay, so let me write down what I have. You can no longer see what's going on here. Let me write down what I get after I'm finished, okay? And I basically have a product. I'm getting a product of matrix elements. Each of them I can represent by a number, okay? Something that is no longer an operator, but is just a function of the variables Pn and Qn, where n is going to be an index running between 0 and capital N. Okay? So let's see what we get in the end. Okay, so so what I'm getting is the following. I get, first I'll get, if I look at this propagator, I'll get QF sandwich with something. Let me not write everything. I just write what you get in the middle. I get something like that. Q n. This is after n. So I'm counting the index n from 0 to capital N. Okay, from right to left. And this is in the n plus 1 step. I get this projector, is that what I wanted? Yeah, okay, so with Pn plus 1 e to the minus it dt. And now I have Pn, Qn e to the minus I v dt, Q n minus 1, and dot, 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 okay? Is it clear? This is somewhere in the middle. I have something like this. This connects to an operator, so let me just focus on the product of 4 objects. And again, each of them is just a number, okay? And now let's write them down. We know exactly what they are. And of course, I forgot something important. Outside of this thing, I have integrals over all these variables, okay? So I have to put here a product of n going from 0 to capital N of dpn dqn. Okay? Okay, it's a multi-dimensional integral. Okay? But this integral will do at the end. Let's see what is inside the integral. And I'm claiming that it's a function that eventually we'll be able to write in a very compact way. Let us first look at these 2 matrix elements of the operators. What is this? I think this you can easily write down, right? Why? Because we said that P is the basis that diagonalizes the kinetic energy. And when I apply this operator, I just get e to the minus I t of Pn dt times, I just get a number times Pn. Right? But
Yeah, half propagator.
what?
half a propagator.
What do you mean by half?
I mean, only for the...
Yeah, it's only for the, I can evolve only with the kinetic energy. But after I do it, let me write it down explicitly. I will have e to the minus I t of Pn dt, it's just a C number, times Pn, and I have to sandwich it with Pn plus 1, right? But because this is a number, I can take it outside of the matrix element. It's just a number, right? A C number. So what I'm left with is the inner product of Pn and Pn plus 1. What is it? It's just a delta, right? It's going to be, because the different P's are an orthonormal basis, right? So this is nothing but e to the minus I t of Pn dt times the delta of n of Pn plus 1, right? Okay, so that's what we get, and then we are actually going to replace this. This Pn will now become Pn. We're going to get only contribution from this Pn sandwich with Q. Okay. So we are done with this matrix element. Now what about this guy? It's the same idea, but now I have two different coordinates, but here I have, so it's going to be, let me just shorten it, it's e to the minus I v of Qn dt times, because I'm now going to get the overlap of Qn and Qn minus 1, it's just delta of Qn minus 1. Okay? So, okay, so that's what I get. And after this delta, actually, I see that I can, let's see what else is left. Now I have here two matrix elements that yeah, I have here two matrix elements, and so okay, what are these? What is this? The overlap of Q and P, or actually maybe it's more transparent to write it like this. PQ is the state P in Q space, in real space, okay? The inner product of P and Q. What is it? This is nothing but the real space representation of the wave function P, right? And we know what it is, because P is a free wave. It's given by some normalization factor that, okay, let's take it to be 1 over times e to the I PQ, right? Remember this from undergraduate. Okay, this is just the projection of the state P of free particle on real space. Okay. So, and therefore, if we switch the roles of P and Q, I just get the remission conjugate, the complex conjugate, which is e to the minus I PQ, right? Okay, now I'm using it here because I have here, let's first look at, this guy, well, because of the delta, we identify Pn plus 1 with Pn, okay? So this is going to be 1 over 2 pi h bar times e to the I Qn plus 1 Pn. Okay? Clear? Similarly, I have another factor like that here. 1 over 2 pi h bar, and but here it's qp, not pq. So there's a e to the minus I of Qn Pn. Okay? Very good. Altogether, what did I get? What do I get? A product of 4 objects. This, and this. I can write them in any order because now they're C number, no more operators. Okay? So let me write compactly what did I get. I'll make some space here. And let me just write down, just for good measure, our definition of dt is t over n, and goes to infinity is dt going to 0. This is something we want to keep in mind. And now I'm writing the result. So in each such, in the nth time step, I'm going to get in the middle of this very, very long string, I'm going to get the following result, and I'm now collecting things a little more compactly. I just, one comment is, yeah, okay, I'm fine. Good, so I'm going to get up to there's some factor of 2 pi h bar, which I keep outside. I'm going to get the following thing. Let me take this exponent times this exponent, and I write them as e to the I Qn plus 1 minus Qn times Pn. Okay? This is just the product of this times this. Then what I'm left with is the exponent of the kinetic energy plus the potential energy, and I can write it as an exponent of the sum because it's a number, right? So let me write it down explicitly. It's e to the minus I h of Pn and Qn dt. When I write h, what is h of Pn and Qn? It's the classical Hamiltonian written as in terms of the coordinated momentum Qn and Pn. Okay, so it's just t of Pn plus v of Qn. Okay? Okay, this is just the product of these two factors. And the deltas only serve to eliminate some of the integrations, right? Because I no longer have Pn plus 1 and Qn minus 1, if you like. Okay? All right, so I get something like this, and of course, this is repeated in the next, what I have to the right and to the left of this, I have exactly the same thing, but with Qn minus 1 and Pn minus 1 and so on until Q0 and P0 on the right and Q capital N, P capital N on the left. Okay? Now let's understand what is this expression telling us. And notice that again, because it's an exponential, these are all exponentials of C numbers, I can write the final result as an exponential of the sum. Okay? Let's first deal with one such term and write it a little differently. Notice that in this exponent, I have here a product of the Hamiltonian times dt. In this exponent, I artificially multiply and divide by dt. I'm always allowed to do it, right? Why did I do it? Maybe you can see.
The action? Action?
In the end, we are going to get, you're jumping a few steps ahead. But this step, what I wanted to, the reason I did it is if I look at this object, okay, and remember that dt goes to 0, okay? This is nothing but qn dot, right? The time derivative of q, okay? So altogether, I can replace this, and notice that after I replace it by I, q dot n pn, and it's also multiplied by dt, okay? So the whole thing can be indeed replaced by just an exponential of what? A q dot p minus h. What is this? This is a Lagrangian, right? So altogether, this factor can be written as e to the I qn dot pn minus h of pn and qn times all that times dt, and this is nothing but the Legendre transform of H, which is the Lagrangian, okay? But this is just one of the terms in the product. I have a product of many, many such things. And again, because it's an exponential of a C number, the product of exponentials is an exponential of the sum. So let's write what is the final result. After I do this, I get the following expression for the propagator. Now I'm writing an expression for the propagator, which is to take this funny operator and sandwich it between a qi and the qf. Okay? So this is what I get. So I get that g of qi, qf, and t is going to be the following. It's an integral, multi-dimensional integral over a product of n going from 0 to capital N of dpn dqn over 2 pi h bar. Actually, I think that, let me just check something. Yeah, actually, sorry, there's just one mistake here. It actually, for the wave function, it should be a square root, so there's only one factor of h bar. Why I see it? Because this has to be the dimensionless. We're talking about the dimensionless quantity, okay? So, sorry about that. So the normalization of the wave function is with the square root of this term, okay? And this was a product of two wave functions, that's why it's one factor of h bar, sorry. Okay, so this is anyway what we get. And then we get, and here there are some constraints on this integral that Q0 has to be Qi, and Q capital N has to be Qf, because in the end we get some deltas of Qi and Q0 and the Qf and Qn, okay? And what is inside the integral? It's e to the sum over n going from 0 to capital N of Qn dot Pn minus h of Pn Qn times dt. Okay? So here I'm writing it formally, assuming a discrete division of the time to slices with finite size dt, and the capital N is a finite number. But now I want to go to the continuum limit. Okay, so I take the limit that n goes to infinity, dt goes to 0, and the stuff that I have in the exponent, I forgot of course the I. Sorry about that, there is an I. Okay, what happens in this limit? The sum becomes an integral. Okay, so what I get in the end is that I have an expression for the propagator that can be written as something that I call d of, let me see how I denoted it. Yeah, it's a d. This is a notation that I will define in a minute. Okay, of e to the minus I. I think there is one thing that I forgot. Sorry. There's one thing that I forgot right from the start. Here I'm basically assumed that h bar equals 1. Okay, so if I want to be very careful, this actually has to be over h bar. There's 1 over h bar everywhere. So let us just write, so this expression actually should be this, and what I'm writing from now on is h bar equals 1. Okay, let's agree, then I don't have to correct it. So they're just for units, I have to divide all the exponents by h bar. Okay, but h bar equals 1, so this gives me an integral, sorry, no minus sign, it's integral from 0 to t dt of L of Q and Q dot, of Q and P, where Q of T Q of T is the limit where n goes to infinity of Qn, and similarly for P. Okay? Okay, so I replace the discrete variables Qn, Pn by Q of t and P of t. They are continuous functions of time. And this is the Lagrangian, which is Q dot P minus H of Q and P, where I plug in the trajectories. So Q and P's are functions of T. Okay? And the integral over time of a Lagrangian is the action. Okay? Now, what is this capital D?
Functional integration, like for each.
So, right, so in fact, exactly, or if you like this, if I want to define it mathematically formally, although for mathematicians don't like everything I'm doing here is dubious, but I have at least one mathematician friend who approved it. So it's the limit when n goes to infinity of this product of exponentials dpn, dqn, and there is a normalization factor 2 pi over h bar. Okay? This is what it is. Okay, and so now so this is what I get, and for some forms of h, I can even solve this integral analytically if, for example, for a free particle, no potential energy, there is no potential, so there's only kinetic energy, but kinetic energy is p squared over 2m. It's a quadratic function of n, of p, sorry, and we know how to solve Gaussian integrals. In fact, this is one of the only integrals we know how to solve exactly. And even if they're multidimensional, it doesn't matter because they're independent, right? Okay, so actually, let me go even one step further, and I have here, the way I've written it here, I still have two variables to integrate over, P and Q. Now, if we're talking about just the Schrödinger equation, the kinetic energy is simple. It's just P squared over 2m. And as I said, this dependent on P is in fact a Gaussian integral, which we can solve exactly. So let's do it. Let's do a partial integration here and do the integrals over the p's. Okay? Only the p, but we will still leave the q dependence. Okay, so this is what you're going to do. Just before that, I forgot to mention that there is, all the time we have to remember that this integral is integrating over all these three variables, that each of them can go from minus infinity to infinity, but at the edges we have that q0 equals qi and q capital N equals qf. Okay, so we have the end and the beginning and the end are fixed by our initial and final. Okay, because we are looking for this particular matrix element. Okay. Okay, so let's do the integration over p. Okay, I think this I can erase. Okay, So I'm looking for particular integral from minus infinity to infinity dp over 2 pi h bar. This is somewhere inside this capital D differential. I have the integral over some p. Okay, so this p is one of the variables along the way, and I have to integrate. Now I'm integrating over everything that depends on p. Okay, everything else depends on some other p and q. So I don't care about it. Just the p dependence. Well, where is the p dependence? I have two terms that depend on p. One is this q dot p, and inside the Hamiltonian I have a p square. So this is a p square over 2m plus some v of q. Okay, this is the Hamiltonian. So what I have to integrate over is e to the I dt q dot p, right? And there's an h bar that I'm setting to 1. E to the, now let me plug in the part with the Hamiltonian. So it's I dt over 2m p square. Okay? Okay, and that's everything that depends on one of the variables p. I didn't forget anything, I hope. Yeah, okay. Now, I'm using the famous formula that, you know, when you have an integral dx e to the minus a x squared plus some bx, the result is 1 over, sorry, it's square root pi over a e to the b squared over 4a. Right? You're familiar with this, I hope. Okay, so this is what I'm using, and the result is, okay, let me just make sure I have the normalization factor right. Now, there is one subtle thing, a bit subtle, but not a big deal. This integral is well defined when a has a positive real component, right? But in our case, actually everything here is imaginary. So you have to be a little careful, but it is still, even if this is pure imaginary, you can still use the Gaussian integral formula. The way to do it carefully, you have to introduce some finite epsilon that is positive and real, but and then take the limit epsilon goes to 0, you get the final result. So it is mathematically well controlled, and the result that you obtain is okay, there's some, this is the normalization factor. It gives some square root, and notice that this expression has I in the denominator, but that's fine. Y is fine. Actually, if we take this factor I outside, or actually square root of I, which eventually I'm going to get a product of many such things, it's going to give some complex number, okay? The complex number is just a phase, okay? The complex part of it has some absolute value, and then there is a phase. And the phase is something we never care about, because any quantum state is defined up to a phase, right? And we know that this propagator that we are calculating is a complex number, right? And we don't really, there's no physical meaning to its phase, because if you want to ask the probability for the particle to arrive at QF, we anyway take the absolute value square, okay? So I'm not intimidated by the fact that I have some non-trivial phases here. What I care more about is the exponent. So the result of this integration is going to be mq dot square dt. There's a factor of 2. Yeah. Okay. And actually there is an h bar, which again I'm setting to 1. Okay. All right. Now what is written here actually in the exponent? mq dot square over 2 is kinetic energy, but it's expressed in terms of a velocity and not momentum. We got rid of the momentum, okay, and we just get the kinetic energy in terms of q dot, and this is the part that came from the kinetic energy. Now everything that is left we still have to integrate over is only the potential, okay? And this just remained. We didn't touch it. We just integrated over P. So after I'm done, I hope you are convinced that I'm going to get the following result. Okay, and here I no longer have a momentum, so let me just leave this here for the definition. I'm going to get that the propagator is an integral over something that I will denote as a functional, now it's really a functional integral over, what am I actually integrating over? I'm integrating over, in the continuum limit, a q of t. So q that originally was a discrete set of variables, qn, now in the continuum limit, it becomes some function of t. Q as a function of t is what we call in classical mechanics a trajectory, okay? And the integral is an integration over all possible trajectories, okay? This is the important conceptual stage here. We are allowing the quantum particle at any time t to explore the entire space, okay? And we allow it, if we look at its time evolution, we are allowing the quantum particle to take any trajectory, and there are only two constraints on the trajectory, that q of 0 will be defined as the initial state, and the q of capital T, which is the final time, is qf, okay? So, yeah?
So the least action in quantum field theory become quantum probability action, least action, something like
right. That. Right. Again, you are jumping 2 steps ahead, but you get to it in just a minute. So let me just finish writing what I have here now in the exponent that I'm integrating over is actually, with your permission, I'm putting here back the h bar just that you'll see how it comes about as a dimensionless thing. Okay, so this is the action. What is the action as defined here? S is the integral from 0 to capital T of the Lagrangian, but now the Lagrangian is written as half m q dot square minus v of q. Okay, where this q and q dot are, q is a function of t. Okay, at any instantaneous time along the time evolution. This is what we have in the experiment.
Okay, and what about the...
Now what is this?
No, the coefficients. We just kind of...
Which coefficients?
The
So this d
we
is...
define it with the coefficient.
Yes, exactly.
Okay.
Exactly. That's right. Actually, we don't really care about them. I mean, of course, you can take it into account. We know exactly what they are, but they're not. They're just look at what this is. Actually, let me also mention something. So here you have a dependence on dt, right? But what is dt? dt is t over n, right? So it depends on t in some way, but we have here a variable capital N that we want to send to infinity. So the formal definition of this thing is the limit when n goes to infinity of the following expression, m over 2 pi h bar, we put the I here, and now instead of dt I write t over n, and all this appears to the power n, okay? Why? Because the same factor I have here, not one Gaussian, a lot of them, capital N. So this is to the power n, okay? It's a very ugly expression, but let's assume it has some well-defined limit, n goes to infinity, and then it's the integral. Sorry, it's the product. It's the product of n going from 0 to n. Actually, if you want to be really careful, there's an n minus 1, but let's not go into it. Of
it's not n like
dq, sorry, dq n.
Shouldn't it be in the power f, because it was inside of the...
No, because you see this factor already came from the integration over p, okay? And the 2 pi h bar,
No, I talked about the power, like it's supposed to be in a root.
Sorry.
F.
Yeah, sorry. Thank you. That's a mistake. Yeah, it's n over 2. Yeah, sorry. Yeah. That's the right factor, exactly. And actually, okay, I want to be really careful. N goes from 1 to n minus 1 because we identified the 0 and the capital N with the initial and final that are fixed. Okay? But in any case, so this prefactor is an ugly thing and all that. But what really determines the behavior of this integral, so eventually we just get, there's some normalization factor, and then there is an integral over an exponential of the action, okay? And the action is a functional of a trajectory, okay? We allow all trajectories, and each trajectory will have some contribution to the action. Okay. And now here comes the thing. So what we're actually doing is the following. Let's interpret physically what is this path integral doing. I have my initial coordinate and I have some final coordinate where I want to see what is the probability or what is the amplitude for my particle to arrive here. What is the path integral really describing? I integrate over all trajectories. So for this particle to go from Qi to Qf, I can go this way. I can go this way, right? I can go use more colors. I can do this. Okay, and there is one trajectory that will be the classical trajectory. What is the classical trajectory? This is, from analytical mechanics. It's the trajectory that gives a minimum to the action. Okay? And
so the mean field?
I don't call it mean field.
Yeah.
It's the minimum action trajectory. It is the so there is a classical trajectory. What is it? Now it depends on the Hamiltonian, on the potential in some way. There is some classical trajectory. A classical particle, if you have initial conditions, you know exactly what will happen. It's completely deterministic. It will follow the classical trajectory, and that's it, right? For a quantum particle, that's not true because it has a wave function and it has some different probabilities to be at different points at different times. In other words, it's allowed to take all the craziest trajectories you can imagine that go from Qi to Qf. Now, each such trajectory will have some contribution to the exponent. Mathematically, the one that gives the minimum to the action will dominate the integral, right? Why? Because here, notice that there is an I here. It's a rapidly oscillating function, okay? And therefore, if you solve it in a saddle point approximation, I don't know if you learned it in in some mathematics course, okay? There is a saddle point approximation, and it suggests that the integral of this form can have an approximate solution determined by the function that minimizes the exponent, okay? Now, when is this a good approximation? It's not always a good approximation, actually, right? So, again, I don't know if you learned it in mathematics. When is it a good approximation? When the exponent is very strongly dependent on the function, right? So, when you have an integral of the following form, I have some integral dx e to the I lambda f of x, and f of x is some function of x. If I have something like that, when there is the parameter lambda is very large, the exponential is strong, or the result of the integral is strongly dominated by the minimum value of f, and decays very fast around it. So in the limit that lambda goes to infinity, that's where the saddle point approximation becomes very good, okay? And what is our lambda in our case? It's the inverse of h bar, okay? So in the so-called semi-classical approximation, where you take h bar to 0, you recover classical mechanics because you get only one trajectory that dominates, and that's that. Okay? What does it mean to take h bar to 0? We know that it has a fixed value of, I don't know, 10 to the minus 34, right? Joule second, right? Or something like that, okay? What we mean by that is that if we have something like a macroscopic object, okay, a tennis ball, then the action, which is combined of things that have anything that has dimensions of action, is much larger than h bar. Okay, and then the ratio becomes a large number. So that's what it means. If we're talking about very massive object or something that is macroscopic, we basically recover classical mechanics. But if the particle is small, and if you cannot neglect it, you cannot take the limit h bar goes to 0, then the corrections are very important, and you get a quantum behavior. But it's a control parameter, and in the semi-classical approximation, you recover it. Otherwise, you get quantum fluctuations, but formally this is an exact expression for the propagator. Okay. So I think from a conceptual point of view, what a Feynman path integral first is a mathematical tool. For some cases, as I said, you can even solve it, and solving it involves doing integrals. You are going to see in the tutorial the example of a free particle, and also in your homework, I think you'll have at least one exercise. So for example, for harmonic oscillator, where the potential is also quadratic, that's another example where it's exactly solvable, okay? But I think conceptually it's more, the conceptual aspect is more important than the tool. I mean, it's not the best way of solving single particle problems, to be honest. Although, again, if you are interested in semi-classical approximation, and in some cases, like when exploring quantum chaos, it's very, very popular. It's very useful to use path integral. But conceptually, the idea is that really what time evolution is for a quantum particle is that it has the freedom to explore any trajectory under the allowed constraints, okay? And the classical trajectory is just a limit case, but in principle, a quantum particle, if it's very, very extended in space, it's the probability that it will hit a particular coordinate in the future is a summation over all possible histories, okay? So that's it. And only when you do the final measurement and project it to a particular Q that you collapse the wave function on something. But the probability to get there accounts for multiple histories in a sense, okay? Okay, so I think this is a great place to take a break. Okay, and then we're going to, and after that I'm going to show you another thing, nice thing that you can do with this. So now I'm going to go one step ahead and talk about a different problem, which mathematically is formally equivalent to this. And it's going to serve us to do calculations in some cases. So the problem is the following. So here I describe this quantum particle, and I was interested in its time evolution. Okay, so the problem was we have a pure quantum state but we prepare some initial conditions for the wave function, and we follow how it evolves in time. So that was the problem that we solved here. Now there is a different question we might want to ask about this particle is a question about not dynamics in real time, but thermodynamics. In thermodynamics, we are interested in computing a partition function, right? So, okay, so let me introduce the problem. So what I'm going to show you now is that the statistical mechanics partition function for a quantum system can also be presented in a path integral form. Okay? So suppose we have a quantum system in a canonical ensemble. It has finite temperature and maybe some other parameters, chemical potential, pressure, but let's just keep temperature constant. And we know that all the physical quantities we want to know about the system we can derive from a partition function, right? So the free energy, the entropy, the specific heat, compressibility, all these things can be expressed as derivatives of the partition function. Okay? Now, what is the formal expression for a partition function? Let me remind you. For a quantum system, okay? It's the following. We have some complete set of states. Let me denote it by lambda. So we have to take the, so let me first write a general expression and then I translate it to quantum mechanics. The definition of Z, the partition function, is a trace over e to the minus beta h, right? Where h is again the Hamiltonian, and beta is the inverse of temperature. Now here, let me just write it like this. So this T, not to be confused with this T, okay, it's temperature, okay? So just to avoid confusion, instead of temperature, we parameterize it by beta, okay? Okay, so this is the definition of a partition function. If we have a quantum system, what is a trace? The operator e to the minus beta h, we can write it as a matrix in some space, okay? We just choose a complete basis, and the definition of a trace is the sum over the diagonal parts, the diagonal terms of the matrix, right? Okay? Okay, so this is what it is. It's a sum over lambda of e to the minus okay. Okay. Good. So this is a formal definition, very general, and when I write it like this, the system I'm talking about may be a single body, many body state, doesn't matter. Some quantum system, suppose we know it's, we have some basis of the, some complete basis of the states. This is what it is, okay? Okay, now let us focus first on a single particle, a single quantum particle. It is a bit funny to talk about statistical physics of a single particle because usually we think of macroscopic ensemble and so on. But let's assume that there is, we know that there is actually the Liouville theorem that if you let a particle evolve in time, let's say you follow an atom in a gas, okay, and let it spend a long time. In the long time limit, the average of the time is equivalent to statistical ensemble, right? So, but we'll see later that what I'm doing now can be also generalized to many particle systems, which is where we really want to do thermodynamics, okay? And we want to do thermodynamics to explore a quantum system also at finite temperature. Remember that all we did up till now, we solved problems where we looked for the eigenstates of a Hamiltonian and the ground state. The ground state is what you get when the temperature is 0, okay? But if there is finite temperature, there will be excitations, and any physical quantity depends also on the excitations, not just the ground state, right? So we want to be able, in principle, to compute something like a specific heat of an interacting fermion gas, okay? Just something like that. Okay, let's now focus on a single particle, just like here. It has a Hamiltonian that contains kinetic plus potential energy, and it's one-dimensional, only one coordinate, one momentum, and therefore we can choose a basis of states that is a complete basis, and it can be anything, but in particular it can be the states Q, right? The states Q are a complete basis. So let's take lambda to be the state characterized by the coordinate, in which case I'm getting that Z is an integral, because Q is a continuous variable, from minus infinity to infinity. Maybe there's some normalization factor that eliminates the dimensions, but I'm usually not interested in it, right? Because the partition function by itself is not physically interesting. What is interesting is the log, right? And so I don't care about, let's forget about this normalization factor. Integral dq, q e to the minus beta h. Okay, so this is what I have to calculate. Now let's resort to mathematics. If I just stare at this matrix element, I notice a great similarity to what I call the propagator here, okay, right? But I have to do some substitutions. So first substitution is that here Qi and Qf are the same, okay? They're both some Q. Then, most important, in the exponent, I don't have a factor of I, right? I have a decaying exponent, whereas here I have minus I have IT over H bar, okay? So, if let's make a formal transformation, a very simple transformation of the time variable, and it is the following. I define time as minus I times tau, where tau is called imaginary time. Okay? So time is of course a real variable. I'm expressing it as something that is, if it was imaginary, will give me once again a real number after I multiply by a factor of minus I. This is called, this transformation, replacing t by minus I tau, is called Wick's rotation. Okay, so it's in fact a rotation in the complex plane. So let's be very imaginative and think that time is extended to the complex plane. We go from the real axis to imaginary axis. Okay? Okay. So mathematically, I'm allowed to do it. If I do it, then I can map. Actually, let me write it like this. It's a transformation. Okay, I map t to minus I tau. By doing so, I map t to minus I, or actually t over h bar, sorry. I map it to minus I, so let me write it like this, to t to minus h bar beta. Right? Okay, and then what I can do is to take the expression that I got for the path integral expression for the propagator and just plug it in. Okay, so instead of t, I plug in minus I h bar beta, and it gives me this exponent. Okay? Okay, so in other words, q e to the minus beta h, q, this matrix element, is equal to, by definition, okay, by definition of the propagator, to g of q, right, because qi equals qf equals some q at time minus I h bar beta. Okay? So there is an imaginary time variable. Notice that h bar beta has units of time, right? Because it's h bar divided by energy. Okay? So this expression is just given by the function g of these three variables. And what I have to do is to take the path integral I derived in the previous hour and plug in these special cases. Okay? And then finally I will have to integrate over q, and it will give me the partition function. Okay? Now, conceptually, what does it mean? Because the propagator describes a time evolution. Okay, so I have some time axis which I evolve, a real time axis which evolves from 0 to t. Now I'm going to have some imaginary time tau. Okay, it's not really time, it it just has units of time, but it is a continuous variable that changes from 0 to h bar beta, okay? And in particular, actually, if we are at 0 temperature, just as a special case, what will be the upper limit here? This h bar beta, when T temperature is 0, beta is infinity. Okay, so the imaginary time, it goes on a finite axis from 0 to beta h bar, but in the special case of 0 temperature, it actually goes all the way to infinity. Okay? All right, so I don't really have to repeat all the stages I did in the last, right? I mean, I could do it, divide the operator to product and steps and blah, 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 blah. I don't have to do it. I just plug in the final result, okay? Let's see what we get. Okay, so I think now I can probably erase this. So we get that the partition function is, actually before I, the partition function is just the integral over Q of what I'm writing. So let me write what this is. So Q e to the minus beta h is an integral over a functional integral over trajectories, quad trajectories, because Q is now parameterized by the imaginary time tau, with constraints that Q of 0 equals Q of beta h bar equals Q, okay? So it's a path integral over or a functional integral over Q of tau of e to the minus s, okay? Actually, let me write it, sorry, it's, let me just write it explicitly, okay? So it is I over h bar times s, right? But what is s? S is, okay, let me first write it like this, and now I'll do it here. So S was integral t from 0 to t, half m q dot square minus v of q. This was S, but now I want to do a change of variables because my variable is not t, it's tau. So I replace dt by minus I d tau, okay? And I replace the limits on tau by 0 and beta h bar. Okay, so this equals, this gives me, okay, when I do this weak rotation, it will give me minus I integral d tau from 0 to beta h bar q dot square minus v of q. Okay, but here I'm not done. I have a q dot here. Q dot is derivative with respect to t. So again, I have to change variables. And I notice that q dot square is, if I write it explicitly, it's derivative with respect to t square, but when I change t to minus I d tau, I get 1 over minus I square, okay, dq d tau, okay? But minus I square is just minus sign, right? So q dot square is minus the derivative of q with respect to tau square. Okay? So this has to be, let me substitute it here. The kinetic part I can write as minus half d tau q square. All right? And then both terms comes with a minus sign. Now let me plug it back into the exponent. In the exponent I have I times minus I, which gives me plus 1. But then there is an overall minus sign on both terms. Okay? So what I get from it is the following, that q e to the minus beta h, q, is the path integral over q of tau of where q0 equals q beta h bar equals q, and e to the minus s which I define it. This is the so-called Euclidean action, which definition is, do this, the definition is, this is short for Euclidean. It's integral d tau from 0 to beta h bar of kinetic energy plus d. Okay, why is it called Euclidean as opposed to Minkowski? Okay, so it's like in relativity, we have a minus sign between the time and space. Here, both terms appear with positive signs. So, in a sense, we are replacing the time variable by something that is space-like. Okay, that's what it means to change the sign here. Okay, but these are all just definitions. Altogether, what we get here is an expression that, once again, for some models we can even solve the integrals exactly, and this is what has to be plugged in the expression for the matrix element between some q and another q. Okay? Now, here I define this path integral where the boundary conditions are that it equals to some specific q. But to get the partition function, I actually can allow Q to be anything. I integrate over all Q's. So I no longer have these constraints, okay? So in fact what I get is very simple. I get that partition function is just integral, unconstrained integral over all possible Q of tau. The only constraint I have here, Q of 0 and Q of beta h bar, they can be equal to any Q. So I'm integrating over all possible Q's and no longer having a constraint, but I do have one constraint, that Q of 0 is equal to Q of beta h bar. Okay, so this is the constraint, and the integral is over the Euclidean action, where the Euclidean action is what I wrote here. Okay, so this is the definition of, it's just a mathematical expression, and this imaginary time is imaginary. You don't have to assign it to some real time, because there is no time. We're describing a static problem, and it's just thermodynamic, not dynamic. But formally, it has this form, okay, where there is a time derivative, okay? One interesting point about this constraint, so what is really the constraint? We are integrating over all the possible trajectories that are parameterized by tau, but all the trajectories have to come back to the same point. Okay, so our time tau, our imaginary time tau, is changing from 0 to beta h bar, but beta h bar, the trajectory at 0 and beta h bar is the same. So the trajectory goes back to itself after you go along this tau. So now, if I think of this time axis or imaginary time axis as some additional coordinate, we imagine the following problem. Our particle appears to live on a cylinder where this direction, which is infinite, the direction of the length of the cylinder is the space. In our case, it's a one-dimensional space, just one coordinate, and tau is okay, let me write it like this. It's going in a circle with the circumference of the circle is beta h bar. Okay, and the trajectory has to go back to itself after. So we are actually, what we're doing is we are looking at all trajectories where so the trajectory, let's say we start from some point, you have some time evolution, it goes around, come back to the same place. Okay, so there are periodic boundary conditions on this coordinate, fictitious coordinate tau, okay? And I keep talking about tau as if it plays the role of an additional coordinate. It's hard to see it in a strictly one-dimensional problem where Q is the space variable is extended. But let us now try to generalize this formalism to a problem which doesn't have just one degree of freedom, but many. Okay? What is this problem? So, the action that I wrote here is an action of a single particle that has coordinate q, and the only thing I'm integrating over is time, right? So I have trajectory, I have a q, the q variable depends only on one variable, it's tau, and the action is the integral over tau, and the path integral is a path as an integration over all possible q of taus, okay? But we learned, if you go back to the first lecture in this course, we showed how to write down Lagrangian and an action for a system that has many degrees of freedom, and I remind you what that was. The elastic string. Remember, this was the first problem we wrote when we started the course, just to show how we go to field operators. Okay? So, and now this is already a problem of many degrees of freedom on which it makes sense to do statistical physics. Okay? Because we no longer have one particle. You can actually think of it as a string, an elastic string of atoms with some elastic forces between them, and the Q now describes not the coordinate in space, it describes the displacement of this string from equilibrium, and this displacement depends both on time and on space, right? So this is what it is. Let me write it here. Okay, so this is the problem of elastic string. In that case, we wrote, I'm just reminding, we had the action was integral of time, okay? This was in the case that you had a time-dependent action of a Lagrangian, and the Lagrangian was integral over space from 0 to L of, let me write down what we got, half m q dot square minus the potential, and the potential energy was not just dependent on it didn't depend on the coordinate itself. It was something we could write as rho s stiffness dxq square. Okay, this is what we got for an elastic string. Okay, more generally you can write Lagrangian that also has some function of q, but this is what we got for vibrations, acoustic vibrations in a string. Okay, so here q is a displacement. Okay, q at any point in space and any time, and x here is a coordinate that goes from 0 to L if it has finite length, okay? It's a displacement. it's no longer a coordinate, it's a dynamical variable. And remember, if we want to quantize this theory, we can define a momentum by taking derivative of Lagrangian to Q dot and and write it as a quantum Hamiltonian. But here we want to stay with the Lagrangian because it's good for us. But this is the time-dependent problem. If we are interested in the statistical mechanics problem, we just have to do this weak rotation from t to imaginary time tau. And all it does is to replace the action by the Euclidean action, where the kinetic energy and potential appear in positive sign, positive relative sign, okay? So let me tell you what you get. I can write down a partition function for this elastic string problem, and this is how it will look like. Okay, let me call it z of beta because it gives me some function of beta, the temperature, which again, if I take the log, I get the free energy, the derivative with respect to of the log with respect to t gives me specific heat, and so on and so forth. And I can write it as a functional integral over the fields which depend on two variables, space and imaginary time. And it has this constraint that Q of 0 has to be Q of beta h bar. Okay, so there are periodic boundary conditions in the imaginary time. It's like this cylinder, okay? Of e to the minus Euclidean action, and this is how it looks like. It's actually, let me just write it as integral of tau from 0 to beta h bar, integral dx from 0 to L, and inside the integral what I have is half m d tau q square plus half rho s grad x q square. This is the theory that I get, okay? And I have to integrate over all the possible trajectories, if you like. Q is a function of two variables, space and time. And actually, if you look at this expression, it's a very special case, by the way, that comes from the fact that we have this acoustic regime where the potential energy is proportional to the square of the gradient in x. But then in the Euclidean action, we have also a quad kinetic energy term that is formally similar to this, right? It's some constant times a square of a derivative with respect to tau, okay? Now, if I remember that the solution which gives a minimum action to this, we already studied in the first lecture. Remember what we got? What gives the minimum action? a solution of a wave equation
The
which
other
describe propagating waves with a well-defined velocity, and the velocity turns out to be square root of rho s over m. Remember, right? So now, if we can change variables here and define, let us define now y to be v times tau, where v is this velocity. And I think it's easy to see that, first of all, what are the dimensions of y? Space again, right? So, so by making change of variables here, we are going to get an expression that appears like a square of a derivative in x, and a square root of a derivative in y, okay? And the integral over x and y goes from x goes to L, and this goes to some other, v times beta h bar, okay? Some other Ly, okay? So what does it look like in short? It looks like something that is completely symmetric in space and time. And the tau plays the role of an additional coordinate, okay? Now, we still have to remember that there's one constraint, that Q of tau has to obey periodic boundary condition in the tau, so it lives on a cylinder. And it really, in this picture, you see there is a compact two-dimensional space. It's compact in one direction, and the other can go to infinity. But in our problem, if L is finite, the length of the cylinder is L, and the circumference is beta h bar times velocity, okay? So we basically mapped a one-dimensional problem with time dependence to a two-dimensional static problem, okay? So tau is really like another dimensions. Moreover, if we are now interested in a problem where space is infinite, let's say that x goes from minus infinity to infinity, and temperature is zero. Temperature is zero corresponds to beta going to infinity. So the length of the y direction is also infinite. And in that case, we actually don't care so much about these boundary conditions, because we just have a two-dimensional infinite space. It's really space-time, but the Euclidean form is really like a two-dimensional space. And the partition function that we get from it is actually equivalent to a two-dimensional problem, okay? And notice that for this simple elastic string in the harmonic limit, these two terms are quadratic. If we go, how actually are we going to solve it? If I really want to solve the integral and get an explicit expression, what do? Because I have derivatives here, I go to Fourier, Fourier space, right? So in Fourier space, the Q of x and tau is going to be replaced by their Fourier components, which are both in x and in tau, and the action will become just a sum over the frequencies, okay? And notice that it will be just, this integral is just a product of independent exponents. That's what's going to be in the Fourier space, okay? Because in real space and time, it's non-local, it has these derivatives. But in Fourier space, it's just separable to a product of frequencies, and we can solve the integral. It's just a Gaussian integral, okay? Okay, so we can actually solve this exactly and give some expression for the partition function. What I want to stress, which is I think very interesting, that tau is like an extra dimension, okay? Now, one of the things that we can do with statistical physics, this model doesn't give it because it's too trivial, but if we have more terms like non-Gaussian terms, we can get something that looks like a Landau theory, which can give us phase transitions, for example, right? Now, in the limit of zero temperature, where we can have an additional, we have an additional dimension that goes all the way to infinity, and we can think of the this statistical physics problem is mapped into a classical problem in dimension larger by 1, okay? So actually, I can generalize this this problem of an elastic medium to a case where I have my elastic medium is in arbitrary dimension in space, right? It doesn't have to be a one-dimensional string. I can also have I don't know, some elastic material in 3 dimensions. What will be the generalization? Okay, in higher dimension, I can have D is the space dimension, okay? So I can have d tau integral over space, okay, of d tau q square plus, now instead of this gradient with respect to x, I'm going to have the gradient, right? And what is the gradient square? It's just d dx square and d dy square and d dz square, and I add another tau, okay? So this looks like an integral in capital D dimensions, where D is D plus 1, okay? Okay, so okay, so this was just to introduce this notion of how to do thermodynamics using a path integral, or how to express it as a path integral. The problem is that the way that we defined it, using Q and P as our initial quantum operators, restricts us to problems, even if we go to a many-body problem. I generalized it into the elastic medium just because that was a case where I have something that is still characterized by a coordinate-like variable, okay? And therefore, we could just copy what we did for a single particle and get this, okay? But this is a very particular many-body problem that, in fact, we don't need all this because we know how to solve it exactly. It doesn't have any phase transition. It's just a Gaussian theory with trivial solutions, okay? What we are really interested in do in general is to find physical observables in a quantum system, quantum many-body system, which is made of quantum particles, possibly with interactions between them. This is a highly non-trivial problem. And in the previous lectures, we learned how in some cases we can find the ground state of such state, and we had to do some approximations. Now I want to be more ambitious and not only study the ground state, also its thermodynamic properties, which are embedded in the partition function. Namely, I want to know how to introduce finite temperature. Okay? And in general, it's a hard problem. Okay? We know how to do it for free bosons and free fermions, right? Because we have the Bose statistics or the Fermi function. This we know for free gas, ideal gas. But we are not interested in ideal gas, we are interested in a general many-body problem. Okay? So I would like to generalize the path integral formalism for many-body Hamiltonians of the type that we discussed in all the previous lectures. Okay? So now I no longer have coordinate and momentum. I have a different set of operators which are the building block of the theory. What are they? A and A dagger, the creation and annihilation operator, in fact, a set of them. And this is the thing that I want to at least start today, okay? I'm going to basically borrow this idea. Eventually, we're going to use this notion of imaginary time and all that, but the first stage is to write a path integral not in terms of coordinate and momentum, but in terms of A and A dagger, which again are non-commuting operators. Okay? And but the philosophy will be exactly the same. Okay? So okay, so let me start. Just erase all this. Okay, so this is going to be I'm going to introduce a new set of states that are going to be useful for us for this purpose, and they are called coherent states. And what are they? So let me first formulate again what are the building blocks of the many-body theory that we discussed so far. We have a problem of some identical particles, either bosons or fermions. We have a vacuum, right? A vacuum state, which we already learned can be chosen as we wish, as some reference state. With respect to the vacuum, we define a set of some creation and annihilation variables, okay? Where lambda, the index lambda includes some quantum number or some quantum state of the single particle states. And these are the building blocks of our theory, because we first have a Hilbert space that we call the Fock space, where the elements of the space are states of the form a product over some lambdas of Heidegger lambda to the power n lambda acting on the vacuum, right? And now, depending on whether they are bosons and fermions, we have the algebra rules that are for fermions. We have anti-commutators, for bosons commutators. But we have our Fock space, and any general many-body state can be written as a superposition of such states. And we have a Hamiltonian, and the Hamiltonian is some functional of A lambdas and it's some function, some combination of these operators. Okay, it includes single body terms that have only A Heidegger. It has two body, and it can have three body and six body, whatever. Okay, but whatever it is, we can fully express it in terms of A's and Heideggers. And we can also represent the wave functions. And so it gives us a complete description of the many-body problem. Whether we can solve it or not is another issue. But the question that we ask now is not to find the ground state, it's not to diagonalize H completely, because the matrix that describe it in Fock space is infinite and huge, right? What I'm interested in is to do thermodynamics. So what I want is to write a path integral expression for Z. Okay? Now, what is the trick? What is the trick? Let us borrow the conceptual trick that we employed for the single particle example to get a path integral. We started from expressing the Hamiltonian in terms of coordinate and momenta. These are two non-commuting objects. And we introduced resolution of identity in terms of the Q states and P states. This allows us, and then we also divided to infinitesimal time steps and write it as a product of many such operators, neglect the commutator, all that we did, but the idea was we chose a set of eigenstates of either P or either T or B, right? We chose eigenstates of the operators from which the Hamiltonian is made, okay? For using Fock space as a basis, instead of P and Q, we have A's and Heidegger. So what we want is now to define, just like in analogy with what we did for the single particle, we want to find eigenstates of A and Heidegger. Okay? In fact, it will be sufficient to introduce eigenstates of the annihilation operator. And these are so-called coherent states. Okay? So let me first define a definition of a coherent state. A coherent state, which we denote as phi, okay, for now I call it phi, is a state where if I take any A alpha, let me denote by alpha the different quantum numbers. A alpha acting on phi gives me phi alpha times the same phi. Namely, the state phi is an eigenstate of A alpha with an eigenvalue phi alpha. Okay? All right, now, first of all, let us recall that A alpha, unlike Q and P that we discussed before, which are Hermitian operators, A alpha is not Hermitian, right? It's not Hermitian. A alpha dagger is its Hermitian conjugate. So because it's not Hermitian, it's these eigenvalues are some complex numbers. Okay. Okay. So this A and A dagger are not operators. They don't have expectation value. Okay. In any Fock state, they don't have an expectation. They don't have an expectation value in any state because they're not Hermitian operators. Okay, they're not physical observable, but they can have some eigenvalues. Okay, now what is this coherent state? First of all, it's easy to see that it cannot be a state with well-defined number of particles, right? Because any annihilation operator always reduces the number of particles by 1, right? So any state that is like a Fock state, it cannot be an eigenstate of A. And actually any state that has well-defined number of particles, when we apply A alpha, we reduce the number by 1, right? So it cannot be a well-defined number. It has to be a superposition of many Fock states with different particle numbers. And in fact, it has to be an infinite superposition. To be more precise, and now for today, I'm only going to focus on bosons, okay? For fermions, we have a problem with all this, and we'll have to do something a bit fancier, okay? But for bosons, let me just remind you that we have these commutators, okay? A dagger is, it's a delta of, this is a delta of alpha prime, and AA is 0, A dagger commutator is also 0, and so on. Okay, but this is what we assume. This is for bosons. Okay. Okay. Having that in mind, I'm now writing a guess for the coherent state, which I think in one of your homeworks you're going to prove is correct. And this is what you have to prove. Okay, this is the definition of a coherent state. And this is true for any alpha. Okay? So somehow the explicit expression for phi has to include all the possible alphas. Okay? Okay, so what is the coherent state? I can write it as an exponential of the sum over all alpha of, let me just check, yeah, so the sum over all alphas of this acting on the vacuum. Okay? And I think sort of easy to see. Okay, we have to do the exercise, but I think it's actually quite easy to see that it gives the right answer. Why? Because if you apply the annihilation operator on this. First of all, it commutes with all the alpha, let me call it alpha prime that are different from alpha. And you get one term where there is a phi alpha A dagger in the exponent. If you use the expansion of the exponent, right, this is an exponential of an operator, it's just an infinite Taylor series. And you will discover that it satisfies this, okay? This you're going to prove. So in fact, we have an explicit expression, and it's easy to see that when I expand it to a power series, it's actually all the possible, it's a superposition of all the possible numbers of bosons of each type, right? That's what it is. Okay. Now there is something funny about this this state. First of all, before I get to it, what I'm writing here is an equation between one vector and another. I can look at its Hermitian conjugate. Okay? Let's see let's conjugate both sides of the equation. What is the conjugate of the left-hand side? So I have to switch phi, so phi goes to from ket to bra, and this becomes A alpha dagger, right? This is the Hermitian conjugate of the left, and on the right-hand side, I have, once again, I have a phi, and it's multiplied by phi alpha bar, where in the next lectures, this is just the standard notation, complex conjugate, this is just a complex number. The complex conjugate, I'm going to denote by a bar instead of a star. Okay, let's agree to this convention. So this is an equality, okay? This is nothing new, but there is another identity that I think you can easily prove, that for the same state phi, if I apply a dagger on phi, okay, so which is not this is just the conjugate of this equation. When I apply a dagger on the same phi, this is actually even easier to prove than this. I get derivative with respect to phi alpha of phi. Okay? I think it's easy to see it, right? If I take the derivative, I just get a dagger times the same thing, okay? Now, this is actually interesting because the phi's are eigenstates of A. They are not eigenstates of A dagger, but if I want to represent A dagger in a basis that diagonalizes A, it has to be written as a derivative, okay? What does it remind us of? It's similar to the relation between coordinate and momentum in the usual case, right? So if I'm writing a state in real space, a state in real space, the momentum operator expressed in real space is a derivative with respect to the coordinate, right? Okay, so this suggests that A and A dagger are to some extent going to replace the Q and P of before, okay? Okay, but there is something funny about these coherent states. And it's the fact that if we look at all the possible coherent states, so when I'm writing a particular coherent state, it is represented by the set of phi's, right? So each phi differs from each other. Each phi is in fact a vector of complex numbers. Okay? Let's think just for simplicity about some discrete basis alpha, which is our quantum numbers. Like for example, spin. There's going to be spin up, spin down. So here I'll have just two terms, and the set of possible phi's is going to be a 2 by 2 vector with complex components, and the components can be any complex number, okay? So the set of phi's define a particular state, coherent state, okay? Now, if I'm looking at some phi and some other state phi prime, what is the difference between them? That it's a different set of phi's, okay? Now, usually we expect that we're going to get an orthonormal basis, that the inner product phi prime, we want it to be some delta of phi prime, okay? But actually it doesn't come out. What we get is that, actually let me just for convenience, let me put the prime here. Okay, so if you compute this overlap, well, the phi, the Bryant cat can be, you can just write the Hermitian conjugate of the same thing. You're going to get e to the sum over alpha, phi alpha bar, phi prime alpha. Okay? This is, you can do an explicit calculation and get it. And what can we say about this factor? It's bigger than 1, right? Or it can be bigger than 1. Actually, okay, in principle, because they are complex numbers, it can be anything. But if we look at the special case, that it's the same phi, okay? Just phi with itself. What do we expect it? Usually you expect it to be 1, right? If it's a normalized state, but it's actually going to be, I'm just plugging in phi prime equal phi, and I get phi alpha bar phi alpha, but what is this? Just phi absolute value square. Okay, so now this is definitely positive. Okay, it's definitely positive. So this is always larger than 1. Okay, and in principle, if I want to normalize it, so it will give me a probability of not bigger than 1, I have to divide by this factor. Okay. Now, the fact that you get, as I define the coherent state, the fact that it's written like this, that it gives this, implies that the coherent states are an over-complete basis. Okay. It's not the usual orthonormal basis, it's an over-complete. Okay? Now, what we are going to do is, and we're going to probably start doing it next week, is to do path integral with this, okay? And let us give a hint of what we want to do, because we really borrow the same concept from what we did in the beginning of today's lecture. First, we're going to divide our time evolution to tiny steps, and then write the operators as exponentials of something that has a small factor dt, which we can take to 0 and neglect commutators and so on. But the important step that allowed us to convert it from operators to numbers was that we introduced a resolution of identity, right? This was the crucial step. We had some operators, okay? Something like that, where O1 and O2 do not commute. And what we did is we said, aha, but we can always place in the middle the operator 1, the identity. And this identity can be resolved in terms of some useful states. What are going to be the useful states here? The coherent states, okay? Because they are eigenstates of the annihilation operator. Now, importantly, remember that in the previous lecture, whenever we wrote a Hamiltonian, like interaction terms and so on, we always write it in a normal ordered form, where all the annihilation operators are on the right. Why do we want it here? Because this will allow us, whenever we have something like an exponential of a normal ordered operator, so all the annihilation operators are on the right, and therefore, if we apply it on some coherent state, they will give me the eigenvalues, okay? Whereas the A daggers will apply on the other side and will give us the phi bars. Okay, so this is sort of the idea. So it will, eventually what we'll get is a path integral over the fields, the complex fields now, phi alphas and phi alpha bar, where in the exponent we'll get something like an action, and it's expressed in terms of the numbers, the complex numbers, phi and phi bar, okay? This is the idea, but the first step in order to get there is to introduce the resolution of identity. And usually, for an orthonormal basis, we write it like this, right? Why is this a resolution of identity? Because the lambda is an orthonormal basis, we know that lambda lambda prime is a delta lambda lambda prime, and lambda with itself give you 1. But here with the coherent state, this will not be correct, okay? So if I just write a sum over phi or integral over phi of phi phi, this is not equal to 1. Why is it not equal to 1? Because phi phi gives me a non-trivial number. So what do I have to do? I have to compensate by dividing by this factor, okay? So let me write the formula for the resolution of identity. And I think this will be a good place to stop. Okay, and here we are actually introducing it with a factor for a reason that you'll see later. Just yeah, okay, let me actually write it as integral, it's an integral over all these variables and I divide it by a factor of pi. Why? Because we're going here to use some formula for Gaussian integrals in the complex plane, and this gives factor of pi that we want to cancel. Okay, so that's just a technical definition, if you like. But here I have to introduce a factor that is nothing but 1 over this exponential. Namely, it's e to the minus sum over alpha phi alpha square, and here I can put my projector. Okay? And now it's easy to see that if you plug it in, for example, when you plug it in between 2 arbitrary coherent states, it will give you the right thing. Okay? And it's an identity. This is really the identity operator. Okay? So what we are going to do next week is just, first of all, we start from expressing this trace similarly to what we did for the single particle as a path integral. We write it as a sandwich between some initial and final state, and then we are going to divide it into time steps, the product of operators, and plug in this resolution of identity many, many times in between. And the result will give us something that is conceptually very similar. It's going to be a path integral over these fields, all these fields, but there will be another index here which represents the time, okay, the time evolution, and the inside the integral is going to be just e to the minus s, where s is going to be the action or the Euclidean action if you're interested in the thermodynamic case, okay? Okay, so I think this is a good place to start. Okay.
שאלה. באופן עקרוני, אנחנו עושים את הפרופ אינטגרל. זה דבר שאני מכיר, עושים אותו הרבה מאוד כשאומרים.
כן, נכון.
אז זה אומר שיש לנו מתכנס.
כן.
אז זה אומר שיש לנו איזה משקול, משום מה, עבור הפילדים הקטנים, כאילו בעניינים הקטנים.
מה זאת אומרת העניינים הקטנים?
זאת אומרת, אם לצורך אנחנו חותכים את זה, יש לנו איזה קאט-אוף שממנו זה כבר מתכנס. אז זה אומר שמתחת לקאט-אוף הזה, יש יותר משמעות לפלייסים.
לא יודעת למה אתה מתכוון, כי בסוף אתה עושה אינטגרל על האקשן כולו, כן?
נכון, אבל הלכה למעשה, אתה לא באמת עושה את זה, כי כשאתה מכניס את זה נומרית, אתה לא באמת מחשב